I'd like to set up and solve for you a detailed problem about a completely inelastic collision between two cars. The essential details are here on the screen. If you want to take a minute and copy them down, then you can follow along by taking notes. The problem involves two cars that collide in a parking lot. The first car has a mass of 1,800 kilograms and it's traveling due east at 15 meters per second. The second car, that has a mass of 1,500 kilograms, is traveling northeast, actually mostly north, 75 degrees north of east at 12 meters per second. And after the collision, the cars stick together and slide away. There are four parts to the problem. We'd like to calculate what the final velocity of the cars is after the collision, and also how much non-conservative work is done on the cars during the collision. We'd like to calculate the magnitude of the change in momentum for each car, and that's so lastly we can estimate the average force each car exerts on the other, given some information about how long the collision takes. The four parts each illustrate a key concept of physics. The first one we're going to approach using conservation of momentum. So although the cars collide on a parking lot that's not frictionless, the collision happens very quickly, and the external forces exerted on the cars don't have long enough time to appreciably change the momentum of each car. Part B is going to be an example of our old friend, the work kinetic energy theorem. In Part C, we're going to calculate the change in momentum of a car just by doing vector analysis, remembering that the change in any quantity is its final value minus its initial value. And lastly, we'll use the impulse momentum theorem in order to calculate the force. So here are the steps. To calculate the velocity of the cars after the collision, you have to do a conservation of momentum. And in order to solve a conservation of momentum problem, you really have to make a before and after drawing, or at least a single drawing that includes the masses and their speeds before and after the collision. So here's the drawing that I made. I also put an XY coordinate system on the drawing. In this case, X represents east and Y represents north. And I tried to draw the vectors approximately to scale. All you have to do is set the initial momentum equal to the final momentum. Well, it's not apparent on the slide, but those P's are boldface, and momentum is a vector. So that's a vector relationship about the final momentum and the initial momentum. And vector relationships aren't really very useful for calculating anything by themselves. In fact, what they mean is you have to do whatever the relation says, but in each dimension separately. So this is a two-dimensional problem with an x-axis and a y-axis. So what we really need to do is set the x component of momentum before and after equal to one another, and that'll give us a truth of the system. And then do the same thing about y components of momentum. That'll give us a second truth of the system. So when momentum is conserved, it's conserved simultaneously in the x and y directions. So all you have to do is tally all the x momentum before the collision and set it equal to the x momentum after the collision. Here's how you would do that. Mass m1 is initially moving all in the x direction. So its momentum is m1v1, the v shown in green. m2 is partly traveling north and partly traveling east, or in this coordinate system, partly traveling in the plus y and partly traveling in the plus x direction. You need to select the x component of the velocity in order to calculate the x component of momentum. So that's m2 v2, but hit with the cosine of the angle in order to select the x component of the velocity, shown in red. After the collision, both cars are stuck together, so their combined mass moves at a common speed equal to, I've called v prime, using prime for things after the collision. But again, we only want the x component of that velocity vector, so that's shown in magenta. So the equation for y is similar, and in fact a little bit simpler. if you want to take a stab at it before continuing, but here's what I get. M1, in fact, doesn't have a component of the momentum directed in the y direction. It's all x. So the only momentum present initially is the momentum carried by car 2, and you need to hit that with the sine of the angle in order to get the y component of that momentum. That's shown in blue. And then after the collision, the same thing is true. The two masses, m1 plus m2, have a common speed v prime, but we need to select the y component of that velocity, and that's shown in cyan. So those two equations, 1 and 2, are true simultaneously. In the next couple of slides, we'll talk about how we could actually solve those equations to figure out what v prime is, the speed after the collision, and what theta prime is, the direction of the velocity vector. So our answer is going to be a magnitude and a direction for the final velocity. All right, so all I did here is substitute numbers into equation 1. And you can verify that I did that correctly, and if you find an error, please let me know. I included the units here as well. So on the left-hand side is just the values substituted and multiplied. And same for equation 2. Now, in order to solve those two equations for v prime and theta prime, I think it's important to simplify them. There's two ways you can simplify them. First, you can combine like terms, and also drop out the units for now. If we have everything in SI units, the answer will come out in SI units. So here's what I get when I simplify things a little bit. For equation 1 at the top, I added the two terms on the left, and the right is unchanged, just dropped off the units. And then I divided both sides of the equation by 10 to the third because that's a common factor to both sides of the equation. And then lastly, I divided both sides by 3.3, and I end up with a very simple equation shown in boxes that tells me what v prime cosine theta prime is. That's the x component of the final velocity. The equation for the y momentum simplifies also in a similar way, and you end up with a fairly simple equation for the y component of the final velocity. So what you have to do now is find a way to solve those two equations simultaneously to get a value for v prime, the speed after the collision, and theta prime, the direction. There's a number of ways you could go about it. You should practice yourself. You could solve the first one, for example, for v prime and stuff it into the second one. But I'll show you a little trick. What I did when I see something that has sine theta on one side of one of the equations and then cosine theta on the one side of the other equation, I realize if I divide the two, I can get tangent theta. So what I did there is I took the second equation and I divided it by the first equation. On the left-hand side, I just divide the numbers. On the right-hand side, I divide v prime sine theta prime by v prime cosine theta prime. The v primes cancel out, and I'm left with tangent of theta prime, which is pretty easy to solve, and I get 28.8 degrees. And then you can stuff that back into either equation 1 or equation 2. I chose equation 1 to find that the speed after the collision is 10.9 meters per second. So to answer the question we started out to answer, the car's final velocity is 11 meters per second, 29 degrees north of east. I guess keep in mind too that I'm after a 2 sig fig answer, so through all the calculations, I keep one extra significant figure. Let's go on to the next part. How much non-conservative work is done on the cars during the collision? Well, you should recognize this as a work kinetic energy theorem problem. It wouldn't be something that you would approach using conservation of energy, because energy definitely is not conserved. If you think about what happens when two cars collide, there's a lot of broken glass and bending metal. The energy it takes to do those things doesn't come back like energy stored in a spring or gravity. So all of that work is non-conservative work. So the way to approach this is to use the work kinetic energy theorem, which says the total work is equal to the change in kinetic energy. And in this case, the total work is just non-conservative work, because the collision happens on a parking lot, which is a level surface, so there's no work done by gravity, and there's also no springs involved. Now you might say there might be some work done by friction, and it wouldn't be wrong to think that. But in the spirit of this problem, we have to keep in mind that the collision happens very quickly. And although friction might do some work, it doesn't do very much work because the cars don't move appreciably and there isn't very much time during the instant that they're colliding. So conservation of momentum gets you across the interval from right before the cars start touching to right after they're all smashed up and moving together. And that's a very short interval of time. So here the total work done is just the non-conservative work. It's the change in kinetic energy, so it should be pretty simple to step through this. You need to subtract. The change in kinetic energy is the final minus the initial. And here are expressions for the final kinetic energy and the initial kinetic energy. The final kinetic energy, you use the formula 1/2 mv squared, but the mass is the sum of the two masses, and the v is the speed that they're moving with after the collision, which we now know. But before the collision, the two masses are moving separately at different speeds, so you have to calculate their kinetic energies individually and add them up. One mistake students make sometimes is to add kinetic energies as though they're vectors, or maybe make a kinetic energy negative. Just try not to make that mistake. Kinetic energy is always positive. You always add them to find the total kinetic energy. In any case, you could have paused the video here and calculated numbers to check my work, but here's what I get. So the answer to this question is the total amount of non-conservative work is negative 1.1 times 10 to the 5th joules. So to put that 1.1 times 10 to the 5th joules of non-conservative work into context, it's interesting to compare that to how much kinetic energy was present in the system begin. So I made the ratio, the work done, delta K, divided by the initial kinetic energy that was present. And you find that that's 37%. So in this particular collision, which is completely inelastic, 37% of the initial kinetic energy is lost in the form of non-conservative work. And different inelastic collisions lose more or less energy than that. But it's important to realize that after a completely inelastic collision, there's always got to be some kinetic energy left over. Let's proceed to part C, and that is to calculate the change in momentum of each car. Well, to calculate the change in momentum, you have to do final momentum minus the initial momentum, the normal way that we do it. But this is a vector relationship, so you can't just subtract like we normally would. You could make a triangle, as we've done in the past, but it's probably just as easy, since we have all of the velocities before and after the collision, to just do this calculation in components. So we would need to calculate the x component of car 1, the change in momentum of car 1, and the y component of the change in momentum of car 1. We can do these things separately. The way we do this is simply write expressions for their components and subtract them, final minus initial. So let's take the x component after the collision. That's m1 v1 prime cosine theta prime. Now it's true that both cars are moving together at the same speed, so you might think you would want to use m1 plus m2 in the place of just m1 in that equation, but that wouldn't really be correct, because here we're focusing on the details of only car 1. We want to know how much did the momentum of car 1 change. So car 1's momentum after the collision is car 1's mass times its speed times cosine of that angle. And car 1's momentum before the collision is just m1 v1. So we have to calculate those things, and you can maybe pause the video and come up with numbers for yourself. Here's what I get. If you just plug in numbers and subtract, you end up with the x and y components of the change in momentum for car 1. So for instance, the x component change is minus 9.8 times 10 to the third, and the y component change is plus 9.45 times 10 to the third kilogram meters per second. So if you want to find the magnitude of the change in momentum of a car, then you have to do the usual thing. here we have the x and y components of a vector, and we want the magnitude. So that's right, you sum the squares and take the square root. So if I plug in the numbers for that, here's what I get, 1.4 times 10 to the fourth. So that answers the question about the change in momentum for car 1. But what about the change in momentum for car 2? Because the question asks for both. But here we can use some logic, and we don't have to go back and recalculate, although you could if you wanted. Look at this collision conserved momentum, which means the total change in momentum of the system was 0. But the change in momentum of each car wasn't 0. The only thing we know is that the change in momentum of both cars added up has to be 0. In other words, if car 1 lost some momentum, car 2 had to gain it. So in collisions, the parts of the system exchange momentum, but the total change in momentum has to be 0. So we can conclude from this that the change in momentum for car 2 is the same as the change in momentum for car 1, but as a vector, it would be in the opposite direction. You know, of course, behind conservation of momentum is lurking Newton's laws of motion, F equals ma, and the action-reaction law. So the reason why these two cars have equal and opposite changes in momentum is because the forces the cars exert on each other during the collision are also equal and opposite. And that's why we want to calculate the change in momentum of one of the cars in the first place. It's because we can use the impulse momentum theorem to get at what force is required to cause that change in momentum. So that's the last question. Given some information about the duration of the collision, so this is the time from when the cars just start touching one another but are still moving separately to when they are moving away from the collision at a shared common speed. Collisions happen very fast. So I estimated 0.85 seconds, and if you've ever been in a car accident, I think you can probably attest that it happens in nearly a blink of an eye. So we're going to use the impulse momentum theorem in order to answer this question. So we use the letter J to be a placeholder for the word impulse. And it's a little bit circular, but all impulse is a change in momentum, delta P. So the impulse momentum theorem simply says that J equals delta P. So we have delta P for one of the cars, so we know what the impulse is. But if you read in the book, you can see that impulse is connected to forces via a very simple equation, that the impulse is equal to average force times the duration that the force is exerted. So we can use the impulse momentum theorem in order to calculate the force because we have the change in momentum of one of the cars, actually of both of the cars, and we've estimated the time of the collision. And since we're after only the magnitude, we can drop the direction part of this and simply say that the magnitude of the average force is the ratio of delta P to delta T. And what ends then is to simply plug in numbers and get an answer. So I get 1.6 times 10 to the fourth newtons. And to answer that question in a complete sentence, we could say each car exerts an average force equal to 1.6 times 10 to the fourth newtons on each other. And using the conversion that 1 newton is 0.225 pounds, I get around 3,700 pounds. And it's important to keep in mind again that these forces are equal and opposite because of Newton's third law. So in summary, here's where we are. We started out with the two cars traveling separately, and they collided and stuck together. We were able to calculate their final velocity. We were able to calculate how much non-conservative work was done on the cars. We were able to calculate the change in momentum for each of the cars, and we could use the change in momentum to estimate the force that each car exerts on the other.